Hey everybody. So this evening we're going to talk about Volcanoes Batholiths and gold. Seems like a little off-target topic, but it isn't. It's related to how you understand the origins of most gold. And so I wanted to kind of go back to that topic of igneous rocks and take a closer look at where gold comes from, because it's worthy of inspection and understanding. I also wanted to kind of tell you we're still working on the tales of lost gold. Haven't given up on that yet, but it's taking a little bit more research. I've got somebody helping me right now with some of that, and it should be fun. But we're probably going to go through it episode by episode, so I wanted to line all that up and then start it in a sequence rather than try to break it all up. And so tonight we're going to talk about volcanoes and gold. Okay, ready for that? And let's check to make sure everybody's on board. Look at the Facebook and make sure that everything's running smoothly. You can check, I'm Prospector Jess here from huntingforgold.com, sourdoughminer.com, and you can also take a look at my channel over on YouTube. It's the Prospector Jess channel, and over here on Facebook we run Hunting FOR Gold. That's the page, as opposed to hunting4gold.com. A little confusing there, but we'll figure it out. So right now we just wanted to kind of make sure everybody's online and everything's going smoothly before we start into this episode. It's going to be kind of busy. System indicates that everything's running smoothly, but I don't see it coming through yet. Oh, there we go. Just started up. Make sure the sound's okay. There we go. Hey, Bob. Welcome. And Byron's here from Sandy, Oregon. Scotty Crick from Idaho is in the house. Awesome. And we got Brad Stevens here from Texas, the great state of Texas. And lights, camera, action, all ready, all good. Okay, says Bob, we're going to go. So let's talk about volcanoes a bit. But I'm not just going to talk about volcanoes. What I wanted to kind of go in on is take a look at this picture on the front. I hinted at it the other night. This is a shot looking down from the airplane. We're probably cruising at about 35,000 feet, looking down on a series of volcanoes that are formed in the Cascades. And they're covered with, snow, and they're also covered, a lot of them with glaciers year-round. So it's one of those things where these things become a really big piece of relief in the overall map of an area. You can tell by looking at these things how they stretch out. Oh, and tonight you're sponsored again by 2020, so check it out. That's about water flow and movement of gold with water flow. So what we're looking at here is these volcanoes, and what I wanted to kind of draw your attention to is just their sheer relief. Let me change my colors here a little bit. So we're looking at these slopes kind of going down here like this from the cones. And one of the things about volcanoes that makes them very distinct is they oftentimes have these sheer walls that move out in radial patterns. There's a very typical characteristic of a volcano. And so when you look at them on a topo map, you're going to see something that looks a bit like this. And then you'll see these concentric rings of isocurves running around that kind of have jagged lines. And the jagged lines typically run down these arms. And so what you'll have is this thing that looks like this, kind of a spider. I'm not drawing it right, but you kind of get the idea. And the same thing would hold true over here. This guy might have a canyon that goes down in here, and so we're going to end up with another one over here. And it sort of rings around and bumps out, comes back in and bumps back out here, and then in and out, and so on. And what's going to happen is these isocontours tell you this is volcanic territory, one. Two, they tell you about what's likely to happen to anything that erodes out of this system. So you want to be aware of those isocontours because, as we've talked about in other episodes, downhill, downstream. So it's going to follow, gold will follow the steepest descent from where it breaks out down to the nearest place where it can start slowing down, which would be a creek, river, or stream that this thing would feed. Typically somewhere out in here or here. Might find some like down in these streams right here and that kind of thing. Now what we're looking for isn't the volcano. It's the volcano has adjacent to it the prospect of having hydrothermal vents and quartz intrusions. That's the thing you're looking for. They also may vary the type of volcano they are. These ones tend to be dacitic in nature, and therefore they're like Mount St. Helens. They're explosive when they erupt. You can get into volcanoes like in Hawaii, which are mostly basaltic in nature, and they tend to flow. They just explode in sloppy, gloppy stuff, and then it comes down the hill and slopes, and it moves so it cools so slowly, and is so incredibly less viscous than these dacitic ones that the lava will actually form a tube and flow all the way to the ocean. Whereas here, this stuff really doesn't even want to flow, period. So it may plug up the top of this volcano, and if that plug forms big enough and hard enough, boom, out goes all kinds of erupted material and an explosive force like you wouldn't believe, you know, on the order of megatons, you know, kind of thing. Volcanoes are a force to be reckoned with when it comes to forces of nature, and big ones have large forces. So what you're looking for isn't so much the forces, it isn't so much that, you know, volcanic explosive nature. It's the potential for intrusions inside the intrusions. Now, I'll get to that in a second here. So is this kind of making it clear? I hope I'm kind of coming through about what we're talking about. So let's kind of keep rolling. Let's go to the, let's see. So what we're eventually going to do is down in one of those canyons below the volcano is going to be some water flow that's going to start moving material from uphill up in these areas. I remember this crazy plot. Uphill in these areas. Boy, it just does not want to, oh, I know why. Hang on one second, folks. I know exactly what's going on here. So up in these areas and moving down through the water flow into these areas where it will settle out. And the idea is that that's where you're going to find your gold potential, your ores and stuff starting to break out and form pockets of gold down in these areas. You might find up in these areas some gold ore in the form of a lode. Now, I'm not getting into that tonight. What I'm getting into is going to be how did it get there in the first place? Not so much how we got here, but how we got here. How did we get this insertion of some material that is high in gold concentrates? And so for that, we'll go to our blackboard for a moment, and we'll draw our handy dandy diagram of what we would call, you know, standard igneous rock formation. Now, igneous simply is a fancy word. It's Latin. It means fire formed. Think of it as, well, this is a great big massive furnace, hotter than your hottest iron forge or steel refinery, hot enough to melt rock that wouldn't normally melt, even in those refineries. Okay, so now what powers that? Well, that's another interesting story, because some of it is gravitational forces having to do with the collapse of iron into the core of the earth, and part of it has to do with the decay of radioactive elements buried underneath us. Yes, there's a great big reactor. It's still running. And so what happens is, as those things decay, they give off heat. Well, guess what makes a really good insulator? Rock. Guess what happens when you have lots of rock around a great big furnace made out of all kinds of, you know, atomic materials? Well, that rock gets hot enough, it starts to melt. Guess where it goes when it melts? Well, if it's dense enough, it goes down. If it's not dense enough, it comes up. So what we're going to start talking about is what happens when it starts coming up. Now let's go back to our fancy color for a volcano. And so what we're going to have is essentially, you know, a surface. Got to draw it like this. This is your landform around the volcanic area before the eruptions start happening. I'm leaving a hole in the middle because this particular interface doesn't allow me to draw very cleanly through that kind of stuff. So this is kind of what our landforms look like, and we'll just leave it at that. These are layers of previously deposited material. It could be igneous, it could be metamorphic, or it could be sedimentary. But it's just rock and soil and sand and whatever else compressed down, and typically goes very deep. You get deep enough, you get to the mantle, okay, which is where we start our story. So now I'm going to take deep in the mantle, I'm going to paint this some really gnarly color like magenta. And so what we're doing here is underneath here is our big huge pot of magma. And what magma is a very dense material, largely high in iron, but it has pretty much every element on the surface of the earth mixed in, including gold, pyrite, in the form of sulfides and whatnot. None of this stuff, you know, if it's reactive, has really done its final reaction and formed into the minerals that it's in yet. It's largely in a fluid state that is more elemental than it is crystalline or compound. And so what happens is, as it starts to come up, things start reacting and the fun begins. So now this thing starts to move up through the surface. Well, if it comes up and punctures the surface and makes its way out the top and starts flowing out of a volcano, okay, that's a surface intrusion, we get our typical volcanic activity, and we can get cones, you can get fissure flows if it's, and the key on a cone is that the material typically is thick enough that it immediately, once it deposits, doesn't move very far away from this origin. If it's a lava flow, like a fissure flow would be, where there's a crack forming, let's have a lava flow here. If there's a crack forming, it may flow out and flow on for a long distance in any direction. Hence, you get like the massive fissure flows of Idaho and so forth. But in this particular case, we're looking at these cascades we were looking at earlier. This stuff just starts to pile up, and you get these massive cones, and in some cases, if the cones are structured right, they become these fairly stable cones of, you know, conical layers. At any moment, though, one of those layers can give way, as happened in Mount St. Helens, and then fun begins, because it means a blowout happens, and all of a sudden something that's under a fair amount of pressure in this region right here finds a way to escape rapidly out the side as a gas, and basically like a bottle of soda, or much more explosive than that, more like a, you know, bunch of TNT. It just fires off and releases a bunch of gas. When that happens, the energy is huge, you know, like I said, megatons kind of thing. So what happens with this under those conditions is that's kind of how that begins. You can also get conditions where one of these might come up, and let's just draw a picture of one that kind of comes up through a fissure crack into this material in between and works its way across, and then sort of bulges out. So we'll fill this thing out like a mushroom. Bulges out, but never breaks the surface, just doesn't quite get up enough pressure, and it leaves this big, you know, kind of layered thing and fills it in with magma that cools off. And what ends up there is this becomes an underground formation that essentially is what was referred to as a laccolith, which simply is a fancy name for a smaller batholith. It's not a big one, and it's also close to the surface, so one of the ways you tell it was a laccolith is that it cooled quicker. Now, one of the things you remember we talked about earlier is the more material there is in the way of rock, the more insulating characteristics, the longer it takes to cool off. The longer something takes to cool, the bigger the crystals are in it. If it cools rapidly, like basalt, the crystals are tiny. So you would expect to see tiny crystals in this flow, intermediate crystals maybe to tiny crystals in this eruptive material, but nothing very big. All of it is fairly microscopic. Takes a hand lens or better to see it. And so that's kind of the idea here, is that this insulative property is very interesting. We'll call it R for resistance. Okay, it's a thermal resistance. So the deeper it is, the longer it takes to cool. So what ends up happening here is eventually this thing kind of, as this source sort of peters out of energy and eruptive capability, it can't push enough energy up, the material locks up above and starts to cool. As it cools, the last things to cool will be down in this area and here, and especially right in this area right here. We're not quite, I'm imagining, I redrew this a little bit. Let's say the mantle's down here, okay? So this area right in here would cool last. Now this area that's cooling last essentially forms a giant boulder called a batholith. These things are the size of the Sierra Nevada, for example. And so what ends up happening is that thing cools very, very slowly, has basically the same chemical composition of what's coming out in the volcanoes, but since it cooled slowly, it looks differently. So you might see dacites and andesites, you might see granites, okay, depending upon the ratio of quartz and other minerals in there. So what we're looking at now is something that cooled very slowly. Now, with all of that said, in all of these cases, we can have hydrothermal cracks forming all through this process and coming up and venting from material that gets combined with waters and whatnot that get released from the rocks as well as from the soils and so forth involved, and essentially bringing metals up here. And it can also inject them as they're coming up into the surrounding rocks or seeding it throughout this batholith, for example, or even in this laccolith. If it's in the material around it, it can find its way into this material. Now, what is likely to happen though is because of the nature of how these hydrothermal vents work, they tend to act like little scavengers and scavenge out more concentrated forms into these hydrothermal vents. If you're looking at the basic rock, the source of the material, like this, what used to be down just above the mantle, the batholith itself, you're going to find a more disseminated kind of gold. It might, because there might be a fissure running through that material, bringing material up, it might have gold lode running through it, sure. But also it might have micro gold throughout. Or the interstitial stuff, this red stuff, might have micro gold that was seeded through it, through metamorphic processes, or through the same thing, hydrothermal cracks. So it kind of gets a mishmash, you know, a lot of fun stuff going on here. But what I wanted to point out was, where do the igneous rocks come from in the first place? How is it this thing ties with gold? Well, the key thing that ties it are these hydrothermal vents and the host rock. Does it have gold in it to start with? Most basaltic material does not have it. If you're looking for gold, you're looking for andesitic, dacitic, or granitic material as a source material, and then lava flows that essentially come from that kind of volcanic activity. And so what you're going to find is, you know, you might find a capstone of basalt, but you typically find very disseminated, very difficult to locate gold. That's why Hawaii is not a real good place to look for gold. On the other hand, if you look at places around, like in the Cascades, there can be a myriad of these sources because it's perforating a lot of metamorphic material, uplifting going on. We've got all kinds of interesting things that cause the gold to maybe even reconcentrate and get even more concentrated in the case of hydrothermal activity, secondary hydrothermal. So this is kind of the fun stuff of igneous rocks, and I just wanted to kind of touch on that for tonight real quickly as a topic, and leave you with that. Is that helping? Yes, Scotty says, Idaho has calderas, got tubes, got lots of rocks. Where would you look first? Well, the thing I would look at first with any of these areas is I would look, you know, because I'm a cheater. Not really. But it's easier to look where people have found gold before. And so I would avail myself of the USGS MRDS. You can look at the sourdoughminer.com/GGM. That shows you how to use that tool to make maps of those areas like there are around the area. And now one of the things you're going to run into in the Idaho area, like some other areas, is there's a mixture of things going on. So you have to be aware of the geology, because it has a lot of these basaltic flows. And then it has, you know, kind of to the east and northeast, it has more of the Rocky Mountain structure where we have uplifting and more exposure of metamorphic and igneous materials that do have a lot of gold. That basaltic stuff doesn't have so much gold. Now, calderas are interesting, and they can disseminate gold by splattering it all over the planet. But mostly what you're going to find is the gold there is introduced through hydrothermal vents. They're, you know, geysers. And so what you're seeing is geysers and mud pots produce gold, and then earthquakes help help cement that. They help agitate the material and cause it to precipitate the gold. So anyway, let's see. Wonder why no gold in Mount Hood area. Okay, not all volcanoes have mineralization or different types of mineralization. That is correct. Now, that doesn't mean that there isn't gold in somewhere in those areas. You know, if you go due east of there and head along the border between there and Washington, you'll find gold to the east. But yes, not all volcanoes have gold. Remember, I talked to you about this. The source material is the key. So when we're looking for gold in these guys, the thing we want to focus on here, I'm going to circle it in blue here, is what are these materials down below like? And do they have gold to start with? Then, are there fissures and other features that would generally inject gold and concentrate it even more so? Those two things are big harbingers of gold. Without them, if you're looking over in this region over here and looking strictly at lava flows and that kind of thing, it's not so interesting. If you're looking at particular kinds of material, if it doesn't have the source material for the gold in it, it's not going to have gold. It can have a volcano and it cannot have gold, hence Hawaii. So it's just that you need to connect the dots, that the gold is in the actual material down below. The question is it concentrated enough, and is it in the right place where there can be some, for example, hydrothermal activity requires there to be a sort of admixture of gold-bearing minerals in a high-pressure fluid combining quartz and water in what's called an acidic solution. But it's under such high pressure. This isn't really a solution like you or I think. Think of it as molten glass. And this stuff, as it moves up, has this habit of, you know, having an a ion-laden solution that will be prone to precipitating the ions out. And if those ions are, you know, metals like gold, silver, platinum, palladium, zinc, lead, you know, you name it, then those things will come out under the right conditions. The key is the conditions. One, are they there? Two, do the conditions exist? You have to have both. It's kind of like, you know, what is it? Fire takes air, you know, a source of heat and some fuel. And without one of those, you can't have fire. Well, with gold, you got to have the chemicals, the conditions, and you have to have them in the right situation for it to precipitate out that gold. Otherwise, you won't have gold, or it'll be disseminated, and you won't be able to find it easily. So that's that. Good question. That was Dan. Let's see, Dan. No, that was Byron Brown. Dan says, this is so good, I'm going to watch this 10 times over tonight. My head is full of this. Well, I'm glad. I didn't mean to fill your head with lava, but, you know, it is one of my passions. Let's see, Brad Stevens, good evening, Jess, from the great state of Texas. So here we are, talking volcanoes and gold, Idaho, and rocks and minerals, and Charles is watching, and Scotty Crick, by the way, my square nail find paid off. Wagon dump, thanks for the tip. Awesome. Post pictures. I want to see the gold you find in that area. Okay? But that's awesome. So we talked about that. Those of you who are unfamiliar with the wagon dump and the square nail, a couple nights ago, check out the video on looking at old historic situations where you might discover some artifact in your hunt, like a square nail or two, and you can sometimes, by doing a little further sleuthing, detect that there was a dump, and therefore there may have been an ore dump as well. In other words, a wagon accident. And that can pay off. That can be a really good thing to find. Awesome. Great to hear. Scotty, I want to see pictures. If you find some stuff, let me know. Even if you don't, show me the pictures of the square nails. Just post them here, or post them into the messenger area, and I'll see what I can do to repost them. But I'd like everybody to be able to see what we're looking at when we're talking about some of these classes we do. So Charles says the notification didn't come through. I give up on Facebook on notifications because it does some weird stuff. In theory, if you're following the page Hunting for Gold, FORGOLD, you should get a notification. I think you also have to turn on some bell somewhere. I need to go find this out. But basically, when you do that, you'll be notified whenever we go live. But I also know that Facebook, for among other things, has been having a horrific time, as have just about anything that uses a service online. Ask me how I know, for the last week and a half, because there's been a major outage in Google's cloud space as well as some of Facebook's own space. They don't talk about it much, but we know online because we see it in email delivery. We see it in things like notifications not going through, or worse, access codes don't get delivered, that kind of stuff. So if you have problems, let me know. Request contacts at huntingforgold.com, and we'll see what we can do to help you out, because we certainly don't intend anything to be going haywire here, but sometimes it does. So Steve is here from Wisconsin, and okay, so Charles says he did all I said, and that still didn't work. So maybe, I don't know, we'll have to take it offline and see if we can find out what's going on there, Charles, because I don't know. I do know that, well, let me think about it a bit and see if I can come up with a solution for us. Might be that we just do something a little different, but I can't think of anything offhand right now, so we'll find out. So this is Igneous Rocks and Gold. Looking for gold from volcanoes and batholiths and other igneous sources. There's also the whole business of, a lot of this picture is actually metamorphic in nature, but, because that's the problem you run into most places, is you find igneous where there's a volcano and it's been erupting for a while and it kind of covers everything up. But, if you go just a little bit away from that zone, it all of a sudden turns, metamorphic and sedimentary in a big hurry. It's just a mishmash. And that's why you want to kind of understand what you're looking at when you're looking at the rocks, why you want to have a hand lens so you can check the crystals and make sense out of what you see. And that's probably it for tonight. I just want to kind of touch bases on that front. Kind of made a mess out of it, but it's fun trying. This Prospector Jess, hunting for gold. And like I said, check out the Sourdough Miner 2020. It's a report on how to look at water flow and gold and how they relate to where gold concentrates. Check that out if you haven't already. And I'll see you tomorrow night. Good prospecting. Prospector Jess, over and out.